Hi guys, welcome back to our lectures on quantum field theory, and this is chapter 7 on Feynman Rules, and this is the first part of this lecture. And along with this lecture, again, I'd like you to read Michio Kaku's quantum field theory, Mandel and Scholl's quantum field theory, and Gross's relativistic quantum mechanics and field theory. In quantum field theory, the mathematics is not really difficult if you have good foundations, but they are very tricky and rigorous. And however, Feynman knows very much of QFT, so he invented what we call Feynman rules. And these rules will be discussed here as an introduction, but later on, as we discuss the different theories like electroweak, quantum chromodynamics later on, we'll be experiencing those rules as they are applied in the theory. And he invented the rules out of the Feynman diagrams that he also invented. So the rules can be thought of as prescription to describe all manner of processes in quantum field theory, and are embodied in a pictorial form called Feynman diagrams. So we will be computing physical parameters for various particle interactions, and most importantly, the probability amplitude that process will occur will be calculated, because these are very important in experimental predictions. In quantum field theory, the amplitudes for particle interactions, like those of decay and scattering events, we use the S matrix for the calculation. So any given physical process can be considered as a transition from an initial state given by this to a final state given by this one. So the transition would be from I to F. I is just initial and F is just final. So this transition happens via the unitary operator, what we call S matrix, and this is this one. So your final state would just be the S matrix operated on the initial state. And by the way, this S matrix is unitary and thus satisfies this. So if you multiply to its transpose, or a transpose is multiplied to it, then it just gives the identity matrix. We have learned from quantum mechanics the time evolution of states is described using the unitary time evolution operator called ut t sub o. So the amplitude would have to evolve from this one, alpha I t sub o, a time t sub o, to a final state, alpha f t. And the amplitude would just be given by this. The initial and final states involve free particles that come from time at negative infinity. They interact and then move off as different free particle at state t equals positive infinity. An element of the S matrix is the limit of uh, this equation, where S from initial to final, which is given by this, is given by this expression here. The notation is usually you have Fi here. It's because you have the final state here and the initial state here. In momentum space, the S matrix is proportional to the amplitude of a given process, which is denoted by mfi for a given process, and this is just given by this expression, where you can see the momentum are used inside as an argument to the Dirac delta, so it implements the conservation of momentum. And the the mfi here can be calculated using Feynman diagrams, and it is specific to a particular process. So you have different amplitudes for different processes. The amplitude mfi is calculated using a perturbative process. So you will have different amplitudes for a process, and then you expand a particular process in a series. And by the way, there is one Feynman diagram for each term in the perturbative expansion. Then you can add all of them to get the total amplitude for a particular process. So suppose you have the same initial and final particle states, and in between them are different processes. So each of those processes will have an amplitude of mi, and so if you want to get the total amplitude, then you have to sum all of them, where it's given by this expression, where your gki here are just the coupling constants for each mi. There will be a Feynman diagram for each mi in the sum. Each amplitude scales by a coupling constant denoted by g, and this is increasing as the order of the order of interaction is also increasing. So for first order, you have k equals 1, and for the second order, you have k equals 2, and so on. So you will have more factors of g for higher orders. And if, of course, your g is very small, then it gets then k gets larger. So therefore, the higher order terms will begin to become negligible, and the sum can be cut off at some n to get a reasonable estimate of the amplitude. And again, this is given by the expression, the total amplitude. Like, for example, in quantum quantum electrodynamics, or QED, the coupling constant is 0.0073, which is a very small number. So if you go higher, it will be close to zero. So like, you can consider the second order, but the third order would be very small. So as factors of the coupling constant appear as products, the terms become small enough that they can be ignored in the calculations, the higher orders. We will show some illustrations later about this calculation. And so we try to review some interactions in quantum mechanics, and we will relate it with what's going on in quantum field theory. So we'll start with this one. We can consider quantum mechanics in three different pictures. The first will be the Schrödinger, the second would be the interaction picture, and then in between those two is the Heisenberg picture. And we use a subscript S for the Schrödinger picture and I for the scope I for the interaction picture. So in quantum mechanics, we can separate or split the Hamiltonian into two parts. A free field Hamiltonian HO, which is time independent, and a time dependent interaction Hamiltonian HI. So here it is. Now, the Schrödinger picture uh, of a state vector is written as this cat S, alpha S, and an operator is denoted by AS. So in this picture, operators are fixed and states evolve in time according to this. So as you're familiar with the Schrödinger equation, so you have a time derivative of the state. It is just equal to the Hamiltonian operating on the state S. This is what we have experienced in quantum mechanics, where H here is a full Hamiltonian. A state vector in the interaction alpha Ti is related to the state vector in the Schrödinger picture via the action of the free particle of the Hamiltonian. And this is just this one here. Now, using the interaction picture, take an intermediate view between the Schrödinger picture and the Heisenberg picture, which moves the time evolution from the states to the operators. And the interaction picture operator AI is related to the Schrödinger picture AS in this manner. Again, the HO here is the free Hamiltonian part of the full Hamiltonian. Now we can differentiate this equation with respect to time to arrive at the dynamical equation for the state. So you have this. So you will have the derivative with respect to time of your state alpha Ti, and this is just of course written in full here. So first get the derivative with respect to time of the first factor here, and then it gives you this one, and then this one will be just given in the previous equation 7.6, so you will have this for this one. So finally, and but for the whole Hamiltonian would just be the sum of HO and HI, so it will just, this one will just cancel with the first term, and so it will give you this one. This is now the derivative with respect to time of alpha I. Of course, alpha is dependent on time. So the time evolution of the states in the interaction picture is now given by this one. So this only means that the time evolution of the states is determined only by the interaction part of the Hamiltonian. Now, let's take a look at the interaction operators and see how they are evolving with time. So we can get the, the derivative of 7.8, which is of course this one here. So if we get the time derivative of AI, and of course AI is given by this one, so we'll be getting three separate derivatives for each term, and so for each factor I mean, and so we will have this will just have to be 0, so as it is time independent, so we will have this one, and of course your AI would be given by this, and this one. This is, you can interchange this one, and so finally you will have the time derivative of the operator AI would just be a commutation between the free Hamiltonian and the AI times, of course, I. Now, summarizing how the Hamiltonian affects time evolution in the interaction space, you have the free Hamiltonian affects time evolution of operators, and the interaction Hamiltonian affects time evolution of states here. By the way, in quantum field theory, the fields themselves are also operators. And looking back at this one, this means that the time evolution of the fields will be characterized by the free field Hamiltonian. And we should remember this because quantum field theory are dealing with the fields. So let's proceed now to another section we call perturbation theory. So in quantum mechanics, the time evolution is described by the unitary operator UTT0, and so it's written according to this expression. And if you differentiate both sides with respect to time, you will get this. But this one It's just a derivative with respect to time of u alpha t sub o. So these are just the same. So if you go back to the previous equations, and so you will have this, the derivative with respect to time of the evolution operator is just the Hamiltonian, interaction Hamiltonian times the evolution operator. Yeah, the factor of I is present. If we go back to 7.11 and setting this t to be, we set t is equal to t sub 0, so we will have, in this case we will have this one. So this means that this only implies that t u0 ut0 t0 is just equal to 1, which is just the identity. So there has been no change in the system in time 0. And by the way, you can rewrite this as partial u, or derivative of u equal to negative I h u dt. So you can take uh, as the you can take uh, this one here, this one, as the initial condition to 7.13, and you can integrate to obtain this one. So this is an integral equation which describes how the u operator changes from time t0 to time t. And this suggests that an iterative refinement in improving the computation of u operator in a series of small steps. So you can still expand this part here. As an illustration, we start with a rough guess, say u sub o, and the first refinement would be u1, and this is given by this. So this is your u0, and then your u1 is on the left side. You can note that there's a large change in going from u0 to u1, so there's a need to keep the refinement from, of course, you can go to u2, and then of course you have u1 on the right side, which is given by this. So you will have a complex expression which is very long. So you have your utt0 here, and you have your, of course, this is the first term, and then but the u in the first term would have to look like this, and then again you have the u u2, and then and so on. You will have a lot of terms. So finally you will have this thing, you will have this. If you go to higher terms. So this is now the series expansion of u t sub 0. So assuming that the time satisfies this one here, so there's time ordering. So we assume that the time satisfies this. So we can write the nth term as this one. So notice that the time here are all the same. Here you have t prime t to the n minus 1, and by doing that you will also have the presence of an n factorial here. So the sum of this, by the way, this is called the Dyson series. So the sum of that would just be your a time evolution operator. But this is too long. We can approximate the solution by cutting off some terms and cutting off the expansion at some suitable number of terms. So you can cut somewhere, because if you have already attained the accuracy of the result of your desired result. Now going back to the states, we will solve this differential equation where the h here is not anymore the full Hamiltonian but only the interaction Hamiltonian, which is time dependent. So if the interaction hi goes to 0, then the states are constant in time, which implies that any transition in the state are due to interactions. So to simplify this notation, we denote the initial state of the system at time t sub 0 as this one, I, just the state I. This is the state of the system at t time equals negative infinity. This is the non-interacting state of the particles prior to the scattering event or any event. So the final state, long after the scattering event, so that will be the limit of alpha t at t going to infinity. This will just be this one here. This is the S matrix of the initial state. It is important to calculate the amplitude for a system in this state to end up in some specific state, which is the final the final state. And the S Fi matrix, that's from that's final from the initial SFI, is denoted by this expression here. This is the component of the S matrix. So this means that the probability of going from the initial state I to final state F for a system that starts in for the system after undergoing some interaction is described by this by S, and your PFI is given by this one here. So here, the state of the system at at time t can be written in an iterative expansion that was used in the Dyson series. With an initial state I, you can start with the first two terms here, and then you can do the series by getting the perturbation of this state, this one, this state. Since SFI is the limit of alpha f u alpha I as t goes to positive infinity, as t sub o goes to negative infinity, and it is written here, this expression. We can rewrite or we can write u in terms of a Dyson series. So we can cast the S matrix as a series. So our S matrix now looks like this one here, which is just the same as the time evolution that we had in quantum mechanics and as we earlier discussed. As a summary, to calculate the amplitude Fsi, this one, use perturbation theory and compute terms to a suitable order to acceptable level of error. In quantum field theory, in theory, it is important to describe processes like the creation of matter and antimatter. Say, for example, this interaction here coming from an initially from two particles, two electrons, and then you will have a final state of four particles, three electrons plus a positron. You have a different set of particles in the initial and in the final state. So this is possible in if you have particles moving at a very high speed or interacting at very high energy. So because the sets of particles change, use terms that annihilate particles in the initial state and create particles in the final state. So, and for the next section, we will be discussing about basics of the Feynman rules. As well, Feynman formulated these rules, and this will be used in calculating amplitudes of processes. We will do that in the next part of this lecture. So that's the end of this lecture, and I hope you understand something. And as again, this is to encourage you that to be able to understand further, you have to make some notes for this lecture.